I'm going to be talking about identification of protein-based biomarkers for gliomas. And this work has been done with one of my MSc students. His name is Single. Okay. So first, let me give you some idea about the data set that was provided by Professor Srivastava's lab. So as you all might know that the gliomas are the most aggressive central nervous system tumors with poor prognosis. World Health Organization categorizes gliomas based on malignancy into 4 grades: grade 1, grade 2, grade 3, and grade 4. Grade 1 being the earliest stage and grade 4 being the most malignant form of glioma. And traditionally, gliomas have been diagnosed either by imaging techniques or by histopathology or both. And in this experiment, a team from Bioscience and Bioengineering Department at IIT Bombay performed screening of sera from healthy controls and various grades of glioma patients using human proteome arrays containing more than 19,000 proteins. Okay. So let's note that the observations were made on 19,000 proteins correspond to each patient. Okay. So in our analysis, we have focused only on grade 4 patients. So we have two classes: healthy patients and the patients who belong to grade 4 category. Okay. And so data consisted of 43 patients. 14 of them belong to certain control group, and the rest of them belong to grade 4 category, right? And each patient is characterized by 19,200 features, that is 19,200 proteins, which consist of human protein microarray data. Further, for each of these 19,200 proteins or features, 2 observations were made at a given point of time. Okay, so 2 observations were made, and what was done was the average of those 2 observations was taken into account. All right. So now let me summarize the data. So we have data on 43 patients, 14 of which are healthy patients, and the remaining 29 patients are grade 4 patients. And for each patient, you have 19,200 observations. Okay, so one can view this as in the form of a matrix containing 14 rows and 19,200 columns. Okay, so in terms of statistics, this 43, sorry, not 14 rows. I actually this thing. Pardon me, 43 rows, because there are number of patients is 43. So there are 43 rows and 19,200 columns. So for each patient, row number 1, there are 19,200 observations. For row number 2, where the patient, the data related to patient 2 resides, that again, that row 2 has 19,200 observations, row 3 has 19,200 observations, and the last row number 43, again has 19,200 observations. So essentially, we are dealing with 43 class 19,200 order matrix. This is the data. The data was provided in this format. Okay. Now, the number of patients is usually denoted by n, and the number of features, or the number of proteins, or the number of let's say covariates, these are denoted by p. So as far as this particular case study is concerned, n is given to be equal to 43, whereas p is given to be equal to 19,200. So it is easy to see that p, which is 19,200, is much larger than n, okay, which is 43. And this type of data, where p is much larger than n, is regarded as big data. Okay, that is one of the definitions of big data. if the number of observations themselves, that number also happens to be very large, in tens of thousands, then again that data is regarded as big data. Okay, so I think let me just first briefly tell you what is big data and what kind of problem it poses. Okay, so let us get some idea about the big data. I'm sure you would have seen this terminology, this phrase earlier. I mean, it has become a buzzword nowadays. So we are entering the era of big data, a term that refers to the explosion of available information or explosion of data. The technological revolution has made information acquisition easy and economical. It has driven a big data movement by the fact that substantial amount of high dimensional or unstructured data are continuously generated and stored. Massive sample size and high dimensionality characterize many contemporary data sets. Okay, so on the next slide, I given you some, few examples of the examples where such data sets arise. For example, in genomics, there have been more than 500,000 microarrays that are publicly available, with each array containing tens of thousands of expression values of molecules. This is one example. In biomedical engineering, there have been tens of thousands of terabytes of functional magnetic resonance images, which are abbreviated as fMRIs, with each image containing more than 500,000 voxel values. Other examples of massive and high dimensional data include unstructured text corpus, social media and financial series, e-commerce data, retail transaction records, and surveillance videos, and etc. etc. So I think we do come across such examples in our day-to-day life. Okay, and these all examples give rise to data which can be regarded as big data. Okay. So so I give you the examples of big data. And so our example, the case study, the data concerning the gliomas, that can be regarded as a big data, because as I mentioned to you, the number of features or the number of proteins, which is equal to 19,200, is much larger than n, which is equal to 43. Okay. Now the objectives or the goals of this high dimensional data analysis, these goals tend to be to build efficient methods that can accurately future observations, or to discover correlations between various features of the data. Now 19,200 features, there must be what you call the multicollinearity that exists between, so they must be correlated with each other. So for a given patient, given that there are 19,200 proteins, they must be interrelated with each other. It's not that making an assumption that they are independent is going to be what you call is very naive. Okay, to consider them to be very independent can be considered to be very naive. All right. And so let's look at the challenges that are posed by the big data. So the big data big data, or data is actually data. The word data can be used as a singular as well as plural. Okay. So the big data are characterized by high dimensionality and large sample size. These high dimensionality brings noise accumulation, spurious correlation, incidental endogeneity. Okay, so it brings in a lot of lot of noise. The noise is present in the data, and that affects the estimates of the parameters. So the parameters, the estimates of the parameters, they are no more robust. Okay, and that is because of this big data, the high dimensionality. Then the correlations between the various variables, they tend to be spurious. Okay, the correlation actually may not exist, but I think artificial correlation is brought out. And then there is an incidental endogeneity. I think I'll explain the term incidental endogeneity. So I'm sure you're familiar with the basic form of the model, namely y is equal to, let's say, alpha plus beta x. Just consider, let's say, linear equation y is equal to alpha plus beta x, and this is a mathematical model. If I add error term to it, then it becomes a statistical or a probabilistic model. So y is a dependent variable, alpha and beta are constants, to unknown constants, they are to be determined, they are to be estimated. X is an independent variable, and epsilon is a random error. Okay, epsilon is a random error. So the question is, why is one required to introduce this term epsilon? I mean, for example, so let's say a person walks from point A to point B. He goes for a walk from point A to point B every day, right? Now the amount of time the person takes from starting from A to B and returning to A, that time required is not always going to be the same for all the days. Okay, I mean, let's say for one day he takes 55 minutes, maybe the next day he might take 56 minutes. Okay, or maybe one day he might take 50 minutes, and that will all depend upon his, maybe the weather conditions, it will depend upon his mood, etc. So what I'm saying, so the point that I'm trying to make is that the equation that you have is not an exact equation. So that's why we need to introduce the error term, and that's why in statistical modeling we consider a model y is equal to alpha plus beta x plus epsilon. We don't stop at considering y is equal to alpha plus beta x, a linear equation. If you are trying to fit a linear equation, let's say fine. I mean, just mathematical equation where no randomness is present, then just simple linear equation will do. But if the random component is present, then one is required to introduce the concept of this error term, and the model becomes y is equal to alpha plus beta x plus epsilon. Okay, as opposed to considering y is equal to alpha plus beta x, which is a mathematical model. For example, if I give you a model y is equal to 1 plus 3x, this is a linear equation in mathematics. I think, I'm sure all of us have studied this. Y is equal to 1 plus 3x. So if I put x equal to 3, I'm going to get y equal to 10. No issues. Okay, everyone, no matter, so I mean, person sitting in Mumbai or person sitting in Delhi, if he puts x equal to 3 in this y is equal to 1 plus 3x, one is bound to get y equal to 10. But the thing is that this is a mathematical equation, but statistical equation is the one in which you are considering y is equal to alpha plus beta x plus epsilon. Okay, and why is this required to be taken? So for example, again, this is my favorite example. Let's say one is teaching a course and there are two students in the class. Okay, and let's say if you ask each of these students how many hours did you invest for this course, it is possible that each student has invested 3 hours per week for this course, but both of them, they don't end up getting the same score in the exam. And the reason they don't, so just like y is equal to 1 plus 3x, x equal to 3, you are bound to get 10. But when I put y is equal to alpha plus beta x plus epsilon, even if both the students have put 3 hours, the scores obtained by them are not going to be same. They are going to be different. Okay, because that has to do with the ability to concentrate during the exam, then grasp of the subject. There are many things, and those things are usually captured by the random error term. Okay, so this is a statistical model, and this is referred to as a simple linear regression model. You might have heard of this. Okay, now I was trying to explain to you the concept of endogeneity. So y is equal to alpha plus beta x plus epsilon. Here, when the x and epsilon, so what happens in big data or in high dimensionality, x and epsilon tend to be correlated. Okay, they tend to be correlated, and that is what this term endogeneity refers to. All right. Then also, the massive samples in big data are typically aggregated from multiple sources at different time points using different technologies, and this creates issues of heterogeneity, experimental variations, statistical biases, and they require more adaptive and robust statistical procedures. So that data may come from various hospitals. Let's say consider Mumbai. Now, Mumbai has, big hospitals like Jaslok, or maybe say Kasturba Hospital, then Nair Hospital. So if the data is coming from 3 different hospitals, this data is going to introduce some more heterogeneity, right? Because the way the data got collected at different locations, maybe there is some variability in that, and so the statistical biases get introduced and so on and so forth. Okay, all right. Now I'm going to present to you two methods. Okay, see, the thing is that this the data again, n is equal to 43 and p is equal to 19,200. So as I already mentioned, this is high dimensional data, because the dimension here p is equal to 19,200 and n is equal to 43. So if you try to fit a standard regression model, y is equal to alpha plus beta 1 x1 plus beta 2 x2 plus beta p xp plus epsilon. Earlier, a while ago, I introduced you to the model y is equal to alpha plus beta x plus epsilon, where there was one dependent variable y and only one independent variable x. But as opposed to having only one independent variable and one dependent variable and one independent variable, if you have one dependent variable and p independent variables, then the regression equation is given by y is equal to alpha plus beta 1 x1 plus beta 2 x2 plus beta p xp plus epsilon, where alpha, beta 1, beta 2, beta p are constants and they need to be estimated using data. Okay, now this model does not perform well when we are dealing with high dimensional data. So we have to resort to some methods which are meant to be used for high dimensional data. So I'm going to present you two methods. One of the method is this called sure independence screening for multiple linear regression model. So SIS stands for sure independence screening. Now let us not get bogged down by this mathematics. Okay, so I'm just going to briefly explain to you in layman's term what this method does. And then I'm going to illustrate the use of this method in the data that I was provided by Professor Srivastava's group. Okay, now what this method does is, so let us again let us talk in terms of this p is equal to 19,200 proteins, and what is the response variable or the dependent variable here? The dependent variable is, it assumes only two values. It assumes values. Let's say it assumes value 0 when the patient is healthy, and it assumes value 1 when the patient belongs to grade 4 category. Okay, so I am considering my dependent variable is 0, 1, and that's how it is. Now what is done is, you try to regress. Now there are 19,200, so one considers one independent variable at a time, and y is regressed on x1. Okay, and the regression is fitted, the coefficient value beta is obtained, intercept is determined, so intercept alpha and beta 1 are obtained. Okay, excuse me. Then the next regressor is next covariate or the independent variable is considered, x2 is considered. Again, y is regressed on x2. You get the estimated value of beta 2. So here in the first step you got the estimated value of beta 1. In the second step you got the estimated value of beta 2, because the data is provided to you. Likewise, you go on determining the estimated value of beta 1, beta 2, beta 3 up to beta 19,200. So you have 19,200 estimated values of betas. Okay, now these 19,000 estimated values of betas, okay, then you try to screen out those values of betas which are statistically insignificant. Okay, so those values, so identify the values of betas which are statistically significant, and the corresponding independent variables are retained in the model. Rest of them are discarded from the model. Okay, that is what this SIS sure independence screening helps us to do. You understood? So I just said y, regress y on x1, you get the coefficient of beta 1, you regress y on x2, fit this regression model, you get beta 2, regress y on x3, you get the beta 3, and so on. So at the end of this exercise, you get 19,200 estimated values of betas. Now all of them are not going to be statistically significant. Okay, so I don't have time to go into explain to you what is meant by estimator being statistically significant. So the value is, so it may not be exactly 0. Okay, the value may be non-zero, but it may still be statistically insignificant, and then it doesn't affect the value of the response variable. Okay, that is what statistical insignificance means. Okay, so out of this 19,200, you try to zero in on to fewer number of estimated betas, and the corresponding independent variables are retained, and that is what sure independence screening helps us to do. Okay, I hope you got this. Okay, now just one second. I think again let's skip all this. Only this property here. This property says that, so this property is saying that this sure independence screening methodology, it makes sure that all the important independent variables, they get retained in the model. Okay, that is with probability 1. With high probability, the most of all these important uh, independent variables, they get retained in the model, and the unimportant ones get removed from the model. That is what this, so that is what this method says. All right, so this is step number 1. That is what we do. Now I think, okay, now see, I just explained to you so I explained to you sure independent screenings, which is abbreviated as SIS. I also explained to you the concept of linear regression. See, linear regression containing one variable. Briefly explained to you the linear regression containing p variables. Y is equal to alpha plus beta 1 x1 plus beta 2 x2 plus beta p xp plus epsilon. Okay, but so but these models are to be used only when this I just mentioned to you, these models are to be used only when your response variable or dependent variable y is continuous. So when you measure the temperature, or when you measure the blood pressure, okay, or you measure the blood level, okay, those values are not integer value, those are continuous values. Okay, so when the dependent variable is continuous, then only the regression models that I mentioned to you can be used. Okay, but when the response variable y is discrete value, when it takes value 0, 1, 2, 3, 4 like that, then one cannot be using these models. I think this will give you misleading results. Okay, so there is something called, there's a class of models which is called generalized linear models. Okay, and in generalized linear models, there is specific model. There is one particular set of models, and those set of models, this set is called the logistic regression models. So logistic regression models is these are to be used when the response variable or the dependent variable y it assumes integer values, or it is categorical in nature. Okay, so for example, in our case, we have two classes. Class 1 is the class of healthy patients, and class 2 is the class of grade 4 patients belong to grade 4, right? Now, so we can assume, we can assign number 0 to class 1 and number 1 to class 2. And that's why this dependent variable takes 2, 0, 1 value. And in this case, I cannot be using the regression models, simple or multiple linear regression, but I should be using logistic regression model. And the form of the logistic regression model, very briefly, let me mention to you, the logistic regression model is log of pi x over 1 minus pi x is equal to alpha plus beta x. So instead of y is equal to alpha plus beta x plus epsilon, now what the model, logistic regression model is specified in the following manner, namely log of pi x over 1 minus pi x is equal to alpha plus beta x. Again, I don't have time to go into why the logistic regression model is defined in this fashion. Okay, I just let me mention to you, on the left hand side I have got log of pi x over 1 minus pi x, and on the right hand side is same thing as the model that I had when I discussed the regression model, namely alpha plus beta x. Now what does pi x denote? This pi x denotes the probability of the dependent random variable is equal to, let's say, 1, that is grade 4 patients, and 1 minus pi will be the probability that the patient is healthy, or the individual is a healthy individual. Okay, so this pi is the probability that an individual belongs to grade 4 category, and 1 minus pi will be the probability that it belongs to the healthy individual category. Okay, so logistic regression. So this is what is mentioned here. So again, I'm going to skip this. Let's not. So this is a general form of the model. Again, I'm not, because time doesn't permit me to do that. So I very briefly explained to you the logistic regression model. All right. Now, see, the thing is that, okay, I think so. since our data, for our data, the patient either belongs to the healthy patient the class, or belongs to the grade 4 category. So again, it's a category. The dependent variable is a categorical variable. So I'm supposed to use the logistic regression model. So the model under consideration is log of pi x over 1 minus pi x is equal to alpha plus beta x, where x is the dependent variable. Okay. Now, so how does SIS apply in case of logistic regression model? So again, the same thing is done. What is done is you consider one protein at a time, try to try to construct the logistic regression using protein number 1. You get hold of the beta 1. Then again, consider protein number 2, try to construct logistic regression model using protein number 2. You get beta 2, estimate of beta 2, and so on. So again, at the end of this exercise, you have estimate of beta 1, estimate of beta 2, estimate of beta 19,200. Excuse me. So you have these estimates. Now out of these 19,200, you retain only those ones which are statistically independent, statistically significant, and you get rid of the remaining betas, or get rid of the remaining the independent variables which are statistically insignificant. Okay, and that is what is done. Now I'll come back to this slide. So I'll come back to this slide if required. Okay, now let us turn our attention to the data, this data analysis that we performed, that I performed with the help of my student for the data that was provided by Professor Srivastava and his group. Okay, so again, so you have 43 patients. So let's look at this. So I have patient 1, patient 2, patient 3, and I have 43 patients. I have constructed the so-called box plots for each patient. So let us understand for patient number 1 how is this constructed. So for patient number 1, I have got 19,200 values of proteins. So patient number 1 is row number 1. There are 19,200 values, right? So using those values, this box plot is constructed. Similarly, for patient 2, I have 19,200 values. This box plot is constructed. For patient 3, this box plot is constructed. So for each patient, I have constructed, for this patient, I have constructed this box plot. Now, this being bit prominent, let's see how to interpret this. Okay, so for example, in this box plot, this represents the smallest value out of these 19,200 values, corresponding to patient number 30. This is 34. This corresponds to patient number 34. So among the 19,200 protein values, this is the smallest one, whatever that corresponds to. This is the largest one. Okay. Then when the values 19,200 values are arranged in the increasing order of magnitude, I locate the 25th percentile. This corresponds to 25th percentile. That means 25% of the observation. Please mark my words. Out of the 19,200, 25% of the observations lie below this observation. This is the 50th percentile. So this is the 25th percentile. So if I drop a perpendicular from here to here, I'll get the value of the protein. And 25% of the protein values are below this particular value. Then 50%. So again, if I drop a perpendicular from here to here, 50% of the protein values for this patient number 34, those values are going to lie below this value. This is 75th percentile. So 75% of the observations are going to they're going to fall below this value, and this is the largest observation. So I hope that so what we have done is we have sort of summarized these values of 19,200 proteins using this box plot. And this box plot gives me the idea about the minimum, maximum, 25th percentile, 50th percentile. Now 50th percentile is also referred to as the median. You might know this. Okay, and 75th percentiles. So it provides me information about these 5 entities. Okay, these 5 entities for these 19,000. So based on this data, so these are called box plots, and they are constructed for all 43 patients. Now question is, what do we gather from this plot? Okay. So what we gather from this plot is that, you know, they I mean, they're sort of dissimilar. You know, they're not comparable. They are not comparable. Look at this. This looks as an what do you call abnormal. This box plot looks abnormal if you compare it with the other box plots. Okay, so maybe this abnormality may be due to the uh, the error in recording the observation, or maybe it may be due to the machine. Okay, so we want to rectify this, and so what we do is, so we adjust for the technical error. So the above figure shows the box plot for each patient after adjusting the technical error. So patients from 1 through 14 are from control group. They're healthy, and the rest of them from grade 4. Okay, so this, I think, now you know what this plot stands for. So now I think, as compared to the previous one, I think this one seems to be behaving all right. Okay, so they seem to be hovering around some middle value, and they unlike this one, unlike this one. So there is no, I mean, they're not hovering around central value, whereas this, by and large, I'm saying, by and large, is okay. So this is performed, and then, okay, now it contains all the, so now what is this? So serial number. Okay, so this is, first column is just serial number 1, 2, 3, 4, 5, 6. It goes up to 934. Okay, and these are protein numbers. So what we did was, we employed the sure independence screening, the methodology, using logistic regression. And why did I use logistic regression? The reason I use logistic regression, because my dependent variable y, it assumes only two values, 0 and 1. It is not continuous. It is 0 if the patient belongs to healthy group of healthy individuals, and it is equal to 1 if it belongs to grade 4 patients. It doesn't measure quantity which lies between. It's a continuous, like, as I mentioned, temperature, or the blood pressure, or whatever, or maybe, you can or blood pressure, blood sugar, or maybe the time taken, for car to travel from A to B. It is not, we don't say that it took 3 hours. It might have taken 3 hours, 35 minutes and 15 seconds. So the point that I'm trying to stress here is that the response variable at hand is a categorical variable. It is 0 or 1. So that sort of prompted us to use the logistic regression model. Okay, so we use the SIS, sure independence screening, in the context of logistic regression. So the SIS can be used in the context of simple linear regression, multiple linear regression model that we discussed. When y is continuous, it can be used in case of logistic regression. It can be used in case of, there is other set of models called log linear models. It can be used in the context of log linear models. So what we have done is, we have used the sure independence screening procedure or methodology in the context of logistic regression models. So what have we achieved? What have we achieved at the end of employing this sure independence screening? So as I told you in the beginning, I mean, in the this thing, intermediate states, I told you that sure independence screening retains important independent variables. In our case, the independent variables are proteins. There are 19,200 proteins. So sure independence screening, this method, it retains the important ones, and it removes the unimportant ones. So what has happened now? When we employ that one, out of 19,200, 934 have got reduced, have got retained, and the remaining ones have got discarded from the analysis now. That is the gain by using the sure independence screening method. And these are the numbers of the proteins which have got retained in the analysis. And these are the corresponding estimates, beta. So I mean, for example, what I did was when I fitted the logistic regression model using this dependent variable, dependent variable number 48. This was the parameter estimate, and it turned out to be statistically significant. Again, I don't have time to go into these numbers, but because of this, looking at this value, I can tell that this value is statistically significant. Again, then 141, again the independent variable, I fitted the logistic regression model. Why? Using the 141th independent variable or the protein number. Again, it turned out to be statistically significant because of this p-value, and so on. So all of these are the corresponding parameter estimates. These are the standard errors. These are the standardized values. So standardized values are obtained. For example, this value is obtained by dividing this by this. You will get this. And this is the corresponding p-value. Again, time does not permit me to tell you what the p-value is and how it is to be interpreted. That's why I'm rushing through it. Okay, so this is whatever I just told you orally is mentioned here. Let me not go over it again. But the takeaway is that using sure independent screening, these many proteins, they get retained. That is the moral of the story. Out of 19,200, so the original data, the dimension was 19,200. It is mind-boggling, and the standard statistical methodologies fail to deal with this type of problem. We wanted to reduce the dimension. So using the sure independent screening, we have brought it down to 934 dimension. Now we are concerned with data which lies in the 934 dimension. That itself is a huge number, no doubt about it. But still, from 19,200 to 934 is a significant reduction in the dimension. Okay, so I hope you understood this. Now this is step number 1. Now what I'm going to do is I am going to now use different method, okay, to further reduce the dimension. Okay, and for that these are the various loss function that one uses, deviance, and the loss function is binomial deviance, and the optimality objective is minimization. Then misclassification rate, this is the misclassification error, abbreviation is class. You try to minimize the error. Okay, maybe I can explain this to you in a short while. Let me first talk about this, and then there are other loss functions like area under the curve. This is not a loss function, and this we look forward to. We look to maximize this. We don't look to minimize this, because area under the curve we try to maximize it. The model, we look for the model where the area gets maximized. Here we look for the model in which the mean squared error gets minimized. Here we look forward to the model which minimizes the mean absolute error, and so on and so forth. Okay, so LASSO elastic neck models tuning parameter. Okay, I think so. What I told you that I want to go back to LASSO. I know I didn't mention to you what LASSO is. Okay, so yeah, right. So what LASSO does is, so LASSO stands for least absolute shrinkage and selection parameter. So again, I'm explaining this to you in the context of regression model, multiple linear regression. I'm not explaining it to you in terms of logistic regression model, because simple linear regression model is the most basic model. Okay, that's why I'm explaining to you. So what now question is, what is, again, for a minute, let us recall what the multiple linear regression model is. Y is equal to alpha plus beta 1 x1 plus beta 2 x2 plus beta p xp plus epsilon, where alpha, beta 1, beta 2, beta p are unknown parameters. Okay, epsilon is the random error, y is the response variable or the dependent variable which is continuous, and x1, x2, xp are independent variables. Okay, now question is how to estimate the parameters. How to estimate the parameters beta 1, beta 2, beta p. So we estimate, so there is a notion of least square estimation, in which, forget about the second term, in which we choose values of beta 1, beta 2, beta p, the ones which minimize this y minus beta x norm 2 square. So summation yi minus the model beta I xi square summation, all that is minimized. So you look for beta 1, beta 2, beta p, the values which minimize this entity, and that is the least square. That's the least square principle. Okay. Now what LASSO does is, LASSO not only minimizes this, it puts constraints on the unknown coefficients. It puts constraint on the unknown coefficients. Okay, and this penalty function is added, and then we add, when we add this L1 penalty function, that is, then this is referred to as the lasso. So that's why it is least absolute shrinkage and selection operator. So, and the role of this is that, what this L1 norm does is it drives many of the coefficients to zero. It drives many of the coefficients to zero. That's what this penalty function does. This second does. This part is only least square estimation principle. This one, and when you add this with L1 norm, this drives many of the coefficients to zero, and that's what we are going to do. So I'm going to skip this, and whatever I just orally mentioned to you, I have mentioned here. Okay. So, and this is what we did. So this was the result of sure independent screening. Then we employ these various, so instead of using one, depending on the regression model, we can use various criteria. So for example, I can use various loss functions. For example, logistic regression, I can use deviance. I can use various these loss functions with those things. Okay, and that is what is done. I have not explained to you what is elastic models. I'll do it in a short while. First, let's concentrate on LASSO. I'm in step number 2 now. I already reduced the dimension from 19,200 to 934 using sure independent screening. My next objective is to further reduce the dimension using LASSO. Okay, and so what does one achieve? Look at this. Now, so using LASSO, so this graph shows the mean binomial deviance. So now I'm concentrating only now. Let's concentrate only on the first loss function, binomial deviance, and this is to be minimized. Okay. So if let me explain everything through this figure, and then I can skip the other figures. Now look at this one. So what have I got on the x-axis? I have got log of lambda, and this is the binomial deviance value. So what is lambda here? Again, let us go back to this model. This is lambda, penalty parameter. Okay, this penalty parameter is also unknown, that is to be chosen. So in this, the betas are to be chosen. Also, lambda is to be chosen suitably. Okay, such that the loss function is minimized. Okay, that is the idea, choosing this one. Here, now look at this, what we have. So various values of lambda log lambda are tried, not lambda. Various values of log lambda are tried out. Lambda is positive, so log lambda is defined, and log lambda could be negative. So we have like this value. This is log lambda, and for each log lambda value, you got the value of the binomial deviance. So the corresponding parameters are estimated, betas are estimated, and then this value is found. And for each value of lambda, this value is found, and then you have this curve using this thing, binomial deviance values, and with upper and lower limit, one standard error. So this is the lower limit, one standard error lower limit. This is the upper, one standard lower limit. Okay. Now, idea is to minimize the binomial deviance, right? So you look for that value of lambda for which the value of binomial deviance, it gets minimized. So let's say, so if I look at, see, this value is the maximum value. I go on decreasing it. So can I locate for this value of log lambda, I get this value of binomial deviance, but there is still some other value of log lambda for which this value is smaller than this. So I locate the value of log lambda for which this is the smallest. Okay, and so that happens to be this. This is the smallest. What does this number represent? Now these numbers are representing the number of independent variables. So if I choose so what is the value of log lambda for which this binomial deviance is smallest? From the picture, it is evident that this is the value of log lambda for which this is minimum. Okay, but what is that model, and what is the corresponding value? What is the corresponding the number of independent variables? So for this, the number of independent variables, that number lies between 9 and 12. So from 934, we have brought it down to a number which lies between 9 and 12. See, now the dimension has got further reduced from 934 to 912. So now we have, so this actually enables this LASSO method with binomial deviance as the loss function enables us to identify proteins, only between 9 to 12 proteins that are relevant for classifying. Please mark my words, 9 to 12 out of 19,1200 proteins, 9 to 12, only 9, between 9 to 12 proteins. I don't know, I can locate the number, but the number lies between 9 and 12. That's why I'm saying that the number of independent variables, that means number of features or number of proteins for us, those 9 to 12 proteins, those proteins enable us to classify an individual into one of the classes. What are the two classes? Class number 1 is the class of healthy patients. Class number 2 is the class of grade 4 patients. Okay, so point is that these, so we have to actually, once we decide that, okay, using this, now we have fixed the loss function here. As far as this loss function is concerned, this is the value of log lambda. Once we have the value of log lambda, from log lambda, value of getting the value of lambda is not difficult. You just exponentiate it. Once you exponentiate it, you get the value of lambda, and for that lambda you can identify the proteins, okay, and that are important for classifying the patients. So this is a classification model that we have arrived at using two steps. Step number 1, we employed the so-called sure independence screen, and step number 2, we employed the LASSO method. Okay. Professor Srivastava, please let me know when, I think, how much time do I have?
No, please take your time.
Okay, fine. All right. Okay. So this is using binomial deviance. Okay, I think again, okay, I'll talk to you about this. All right. Now, so again, let us just concentrate on binomial deviance. Let's stick to this loss function. Okay. So binomial deviance again. So maybe I think let me briefly tell you binomial deviance. Now again, see, if you have two classes, P is the probability of an individual getting classified into a class of healthy patients, and one, or maybe class of grade 4 patients, and 1 minus P is the probability of an individual getting classified as healthy patient. Okay, so this, whether you use P1 minus P, it hardly matters. It's just it's just a label. Okay, fine. Now what I'm trying to tell you is that, so how is binomial deviance defined? The binomial deviance is defined as P times log P plus 1 minus P times log 1 minus P. That is how, I think the question that probably must have come to your mind is, how is binomial deviance defined? So for two classes, you have P times log P plus 1 minus P times log P. If you have M classes, if you have 4 classes, class 0 is the class of healthy patients, class 1 is the class of grade 1 patients, class 2 is the class of grade 2 patients, class 3 is the class of grade 3 patients, class 4 is the class of grade 4 patients. So you have 5 classes. Then in this case, binomial deviance will be defined as P1 times log P1 plus P2 times log P2 plus P3 times log P3 plus P4 times log P4 plus P5 times log 5, where P1, P2, P3, 5, P4, P5 are such that they lie, all of them lie between 0 and 1, and they sum up to 1. Okay, so I hope I've given you some idea about how is binomial deviance defined. Okay, fine. Now look at this. So if you use the binomial deviance as the loss function, and if using the two steps SIS and LASSO with L1 penalty, it throws up this model. So how many? It says, okay, 9. I said 9 to 12 independent variables or 9 to 12 proteins. So this is the intercept term in the model. So my model is log of pi x or 1 minus pi x is equal to constant. 1 second. This is constant plus this coefficient times this protein, then plus this coefficient times this protein, this coefficient times this protein, and so on. So how many proteins have I got in the model? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So dimension from 19,200 has got reduced to dimension 10. Okay, and that is if you use this loss function, binomial deviance, and if you use LASSO. If you use misclassification rate as the loss function, then it leads us to this model with these many independent variables, independent features, or in our in the problem parlance, this is number of proteins. This is if you use area, sorry, I mean if you use area under the curve, it leads us to this model with these many independent features. For mean squared error, if you use that loss function, it gives us model with these many proteins and this model. So now see, okay, so we have built these models using various loss functions. Now, of course, we have to see whether these models are, I mean, whether they are robust, whether they are effective or not. All right. So whether they are serving our purpose. So if as and when the new observations become available, what I mean is out of this 43, maybe you can keep us out of 43, maybe 80% of the data, the patient's data is used for building these models, and 20% is used for testing these models. Okay, to test the models, right? Then as and when the new observation becomes available, so new observation becomes available, that means I am given the data about the data for a patient, and I have observations on 19,200 proteins. Now please note that this new patient, 19,200 proteins, the data is available on these 19,200 proteins. If I have to use these models, I don't have to take into account all these values. I just concentrate. If I'm going to use the loss function as the binomial deviance, I'm just going to concentrate on these 10 proteins. I'm going to take out only those values corresponding to these 10 proteins. Okay, I'm going to plug in those values in the model, and based on that, I'll get the probability. So I get log of pi x or 1 minus pi x, I'll get some value, and using this equation, I'll obtain the value of pi x, which is the probability. So that based on the value of probability, the probability value is larger than 0.5, then I'll say maybe it can be classified as a healthy patient, or it can be classified as a, depending upon the value of pi x, I will classify the patient as a healthy patient or a grade 4 patient. You understand the power of these models. That is how it is to be used. Okay, I hope I've been able to convey the modeling aspects, statistical modeling aspects of this data. Okay, now let's change the this thing, what do you call the loss function. Now I'm using the misclassification error as the loss function. Okay, and then the graph shows the mean classification error for LASSO up with upper and lower limit. So again, misclassification error is obtained for each value of log lambda, and then I try to locate the value of lambda for which this misclassification error happens to be the smallest. Okay, so this if you compare all these values, this value happens to be the smallest. I locate that log lambda, I look at the corresponding determine this again tells me that the number of independent features, number of independent protein, that number lies between 13 and 18, and I come up with a model. Okay, so this is using the misclassification error. Now, if I use the area under the curve, if I use the area under the curve, the loss function, and then area under the curve, the optimization problem is maximize the area under the curve, and then you get this. Now, I look for the value of lambda where the maximum value occurs. Okay, and for that value, number of independent features is 70. Okay, and this is repeated like this. Then I use mean squared error. Again, I get similar. So I don't have to interpret now these plots for you. I have interpreted one in detail. Okay, so I hope this is understood. And likewise, I do it for LASSO with upper and lower limit, etc. One standard error. Okay, this is mean absolute error. And the information is summarized in this table. These are the values of lambda for various loss functions. This is the cross-validation mean value of the corresponding loss function deviance. This is the cross-validation standard deviation, cross-validation value, standard deviation value. This is the cross-validation upper limit. This is the cross-validation lower limit. Okay, and there are some important efficiency measures for LASSO for each loss function. And then again, this table has values coefficient correspond to proteins written using the elastic net under different loss functions. Okay, now what is difference between lasso and elastic net? Now, for a minute, let's note that. See, I'll tell you 1 second. Just I'm not using lasso. I'm using elastic net. So how is elastic net different from lasso? Okay, see the lasso. In lasso, one the L1 norm. Then in regression to use the multicollinearity to take care of the multicollinearity, one uses the L2 norm. And if you use the convex combination of L1 norm and L2 norm, that is referred to as the elastic net. So instead of lambda times norm of the beta 1, I have lambda times alpha times norm of beta 1 plus 1 minus alpha times norm of beta 2. That is elastic net, and those results are also obtained. Similar, what is done? Yeah, these are obtained using elastic net. Hello?
You're audible. Yeah. Can hear you. Please turn off your microphone. There's some background coming.
Professor Srivastava, are you trying to say something?
No, please go ahead. I think there was some background coming, so I just told the participants to turn off their microphones.
Okay, fine. Okay. So this is I'll be done in a few minutes now. Okay.
Sure.
Sure. So this is this summarizes the information about. So for example, what these two columns tell us. These columns contain information about the intercept. The model will have intercepts a log of pi x or 1 minus pi x is equal to intercept plus this coefficient times the protein plus this coefficient times the second protein plus this coefficient times this protein and so on. So this is using the elastic net as opposed to using the L1 norm. You're using the convex combination of L1 norm and L2 norm, and you get these various models. Okay. Again, this is done in 2 steps. You have one has employed sure independent screening approach to reduce the dimension, and after having used that, after having reduced the dimension, one in step 2, one tries to further reduce the dimension using elastic net approach. Okay, that is what is done. All right. Again, I think one important thing comment I want to make here is this. Yeah, look at this. If you look at this, majority of these things are getting repeated here. Okay. So the question that should cross your mind is, there are 5 different loss functions are giving rise to 5 different models. Which one to be used? Actually, okay. So in statistical the modeling exercise, we always tell students that we should look for the model which is parsimonious. The model is parsimonious. That means the model, you should look for a model which has fewer number of independent variables. Because the model with fewer number of independent variables, fewer number of these variables is easy to interpret. That's why we look for a model which is parsimonious. Okay, but I mean that is not the only criterion for selection of the model. The model must be, it should have a minimum classification rate, etc., etc. So it has to have other properties too. But one of the criteria is that the model has to be a parsimonious model, must contain fewer number of independent variables, or fewer number of features, or fewer number of proteins. Okay. So that I forgot to mention. So that's why I went back. Is using the same thing whatever we did. This was using the elastic net. This was using the elastic net, and then for various loss functions we have summarized the information here. Lambda values, these are the lambda values. Then this is the mean of this is the let's see, what is this, mean of deviance, value of the deviance using cross validation. Mean of the standard deviation value using the cross validation. See, cross validation, what one does is, again, just let me briefly mention to you. See, supposing you have 50 observations, okay, and if you are, what you are doing is, if you are or maybe let me illustrate with the fewer number of, if you have only 10 observations, and if you are using one-fold cross validation. So what one does is one uses 9 observations to build a model, and 1 observation is used for testing. And the error that is there, that is kept, that gets recorded, that is recorded. Then you take the first 9 values. The first 9 values are, last one is left out for testing. In the second exercise, you leave out the penultimate observation and use the remaining ones to build the model, and then the value of the loss function that you get, that gets recorded, so on. And you repeat this exercise 10 times. You have 10 values of the loss function. So their mean value is recorded here. Mean value of the binomial deviance is recorded here. Then 10 values will have variance. Then its square root will be the standard deviation. Using that, one can determine the upper limit. One can determine the lower limit. That's how these values are arrived at. Okay. Yeah. Then these are the these are the similar plots for the corresponding elastic net for other loss function, binomial deviance, misclassification error, area under the curve, mean squared error, mean absolute error. Okay, now this is the table of accuracy, specificity, sensitivity for all models and loss functions. So on this here you have parameter values, deviance, classes, misclassification rate, area under the curve, mean squared error, and mean absolute error, absolute deviation error. Excuse me. Now, so what have we got? What have we got here? Here, LASSO is used, and in 2 steps. It's your independent screen, step number 1. Step number 2, LASSO with only L1 penalty, and the accuracy value is this much. For this it is this, etc. LASSO, again, when you use 2 steps, in 2 steps, the specificity is this value and so on, and sensitivity is this. If you use elastic net as opposed to using LASSO, the penalty function is not only L1 norm, but it's a convex combination of L1 and L2 norm. If you use that, the values of accuracy, specificity, sensitivity for various loss functions, these values turn out to be like this. Then if you use LASSO for all variables, so in these last 2, what I did was, or what we did was, me and my student, we did not perform SIS at all. We skipped that step and we went ahead and we applied the LASSO for all by considering all 19,200. And you can see the values of accuracy, specificity, and this thing. So these models are so inferior to these models. Again, this model, elastic net was used. So the convex combination of L1 and L2 norm. And again, these values are inferior to these values. Okay, so again, the point of mentioning this here is that, so why did these models become inferior? Why they become inferior? They become inferior because of the dimension. You are dealing with 19,200, that dimension, and this high dimensional data, it brought in the problems like spurious correlation, noise. It brought in noise, and that's why these parameters, look at this parameter, they have got affected. Okay, they have got affected. So I hope I'm able to drive home the point. Drive home the point. Yeah. Okay. So that is what it is, and this is summarized in the next slide. So models obtained using 2-step screening, SIS and LASSO, turn out to be better than those based on only LASSO, or the models obtained using 2-step screening, SIS and elastic net, turn out to be better than only elastic net. We can ignore all elastic net models, only consider only LASSO models. Again, so the question probably is, why am I saying this? What is being recommended is that the models containing elastic nets can be ignored. Now, if you compare this with this, okay, these values are superior to these values. So then why am I saying this? I'm saying this because these models are turning out to be parsimonious as compared to this. That's why I'm saying that although these values are bigger than these values, maybe these models are parsimonious, and that's why it is recommended that these models be used. Okay. So among the shortlisted 2-step models, the models corresponding to binomial deviance loss function look to be parsimonious, and that it is underperforming compared to other loss function results. So deviance models are also dropped. So we can conclude that any of the models among two-step screening with LASSO, depending on which loss function except binomial deviance, is to be optimized. Okay. And these are the references. I'll be happy to take any question that you may have.